thank you everyone for coming to the education night tonight. Just first off, I just want to remind people that we do have our biannual conference in October coming up, and there is a submission, expressions of interest to submit a presentation for that conference. So please head on over to the website, and if you've got a presentation or an abstract, please send it on over for review. Tonight we've got Dr. Henry Liu. He's going to do a presentation for us on fire modelling, in particular the fire at Quakers Hill. I'll let him introduce himself. So thanks, Henry. Take it away.
Thank you so much, Mark. My name is Henry Liu. You can call me Henry. Chinese name Henry doesn't really matter. Sounds very similar. And my presentation today will be fire engineering with computational fluid dynamics. And thanks, Mark, for his introduction. And actually, the Quakers Hill fire, that fire scene is coming from my supervisor, PhD supervisor. He did the study around 10 years ago while he was doing his PhD, but I'm glad that I can share that with you as well. I assume that possibly some of you listening actually went into the fire scene investigation yourself, or probably your colleague did it. So it's a great opportunity for me later on as well to gain more knowledge from your perspective as well. So without further ado, a bit of my, presentation here. Let me draw on the laser. So a bit of a presentation online today will be a very short background and a bit of intro of myself. The main content today, I will basically divide it into 3 to 4 sections. Fire engineering practice with computational fluid dynamics, we recall CFD. So the topics will be on fire suppression. This is my some work that I've done during my PhD, and radiation heat floods and smoke movement. These 2 are the work we've done with Fahrenheit Global. So they are real world scenarios and real world problems. Basically, I want to demonstrate how we can use computational fluid dynamics, use this powerful tool to aid in our real world life instead of like purely on research, but an engineering approach. The last and foremost is the application in arson fire scene investigation. As I've labeled it out, the credit goes to my supervisor, Dr. Anthony Yun, and we will be coming to that later on. And I will break these 4 sections down, so one by one. We can follow up by a Q&A by one, or we can have the Q&A at the very last. Depending on your preferences, we can go and find it out. So a bit of myself, as I introduced, as Mark introduced as well, my name is Henry. I'm right now working at Fahrenheit Global. My email address here. So if you have any questions later on, if you want to know more about anything, feel free to drop me an email. I obtained my PhD in mechanical engineering in UNSW Sydney, actually in 2022, so basically 1.5 years ago. After my PhD, I continued research as a postdoc research fellow in both UNSW and Macquarie University. And I'm, as I said, right now a fire engineering consultant at Fahrenheit Global. At the same time, I'm an adjunct fellow at UNSW Sydney, a lead guest editor of a SCI journal at DPI Fire. And so if you are actually willing to submit in some academic journals, we have some ways as well. So the work I do is mainly on computational, so CFD ways in terms of fire engineering and computational multiphase flow. And about the multiphase flow part, I will be demonstrating a little bit more of it in the fire suppression part. And I also do hydrogen safety as a part of my research, but this is kind of out of scope of today's presentation. But if you are interested, we can talk about it more in later perspectives as well. Research partners, I have collaboration with my group back in UNSW, collaboration with my postdoc supervisor, Professor Fatima, back in Macquarie University, and my PhD supervisor right now went to Hong Kong Polytechnic University in Hong Kong. So we have collaborations in mainly these 3 universities, but we have also other universities coming in. We have collaborations and friends in everywhere anyways. So a bit of outline. So first topic gonna be, like I said, fire suppression. So fire suppression mechanism is basically what I am interested in while I enrolled or entered my PhD program. So to know how to suppress a fire or to know how fire is suppressed, we have basically to know, okay, where is the origin of the fire, or how does the fire start? So if we look at on the right-hand side, this is a typical fire triangle, or the fire four essential elements to form a flaming fire. Basically, the triangle will be heat, oxygen, and fuel. And all these three combined is actually the fire, is essentially a very significant chemical reaction, or very severe chemical reaction. That's actually the fire itself. It's chemical reaction. So if we remove any one of these elements, the chemical reaction won't sustain. So the fire will be suppressed. So knowing that, we basically just need to know, okay, we remove or we crack one of these ones. So the first thing first is, okay, why now we remove heat, the application will be like fire sprinklers. So the removing heat from the combustion surface, or from the flame region, or from the heated region, for example, like battery fires, something like that. So as long as we reduce the temperature, remove the heat, chemical reaction stops. So we have a suppressed fire. Secondly, if we actually displace the volume, replace the reaction zone with something non-reactable, basically say we get rid of the fuel, or we get rid of the oxygen, so we have basically a dilution. The typical example of that is water mist system, which actually repels the fuel and repels the oxygen via basically water vapor, which is not reactable, which is not combustible as well. So basically, that's the way water mist can come into play. And separation as well, separation isolation, basically we are removing both oxygen and the fuel away. Basically, we're stopping them from contacting. So a typical example will be the fire curtain. And what I will talk about more is about the difference between sprinkler and water mist system. So next slide. And the sprinkler system and water mist system, as we know, the most significant difference between these two systems is their droplet size. So on the right-hand side, again, you can see I've made a comparison. And the average water droplet coming from a sprinkler system is around 1,000 micrometer. But on the contrary, an average or typical water droplet coming from the water mist system is just around 100 micrometer. So you see, in terms of the area, projection area is already such a huge difference. But if you imagine on the volume, it's actually triple the difference as well. So actually it's this significant difference in terms of their volume or the size of the droplet made the significant difference on the fire suppression mechanism for sprinkler and water mist system. So for sprinkler system, actually we said it's a flooding system. So basically when a sprinkler activates, it flooded the whole area. But for water mist system, it's more acting in the clouding or evaporating sense. And some cons and pros about these two systems is that for sprinkler systems, we need a pressurized pipe system, and we need probably a larger amount of water supply. And we need a water storage if we don't really connect the pipes to a town main, and it actually produces a larger droplets. But on the other side, water mist system is quite more expensive compared to a sprinkler system, and they produce smaller droplets, and basically they are more expensive because they have dedicated nozzles, or they have high pressure gases to drive the water mist or to break down the droplets. So that's what we call a twin fluid system. And probably you will need external energy supply to break down the water to smaller droplets as well. So either the external energy supply being a compressed gas tank, or some other form like electrical pumps or something like that. So that's the cons of water mist systems. And I've labeled actually the CP and latent heat. That's for later usage as well. But just give you an idea, the CP or specific heat of water is around 4.18 kilojoule per kilogram K. But the latent heat capacity of water is around 2,200. It's basically 1,000 times of it, the heat capacity. So it absorbs heat. The methodology we are going to use, or I actually used during my PhD, for the majority of my PhD, is the Eulerian-Lagrangian method, which actually is in the field of the computational multiphase flow. So what we call it a multiphase flow is if you can imagine the background air or the environment we are staying at is one phase because it's basically gas. We call it gas phase. But water droplets, we know it's water and it's droplets as well. So the droplets moves within the space or within the air. So that's the second phase. So we call it actually a multi-phase flow problem. And Eulerian-Lagrangian, the terminology here is that Eulerian is, if you imagine there is a Cartesian system, X and Y and Z, but this Cartesian is fixed, being say like 0, 0, 0 as your background system. But we have a Cartesian system for each and one of these droplets. So this Cartesian moves along with this droplet. So with the background and with the droplets. So we have two different, or actually many different Cartesian systems depending on how many droplets you have. So each one of these droplet systems has its own referencing system, but the background is another fixed Cartesian system. So that's Eulerian, that's Lagrangian. So to a bit of a background knowledge here. So the beauty of Eulerian-Lagrangian is it allows us actually to track each and every one of these droplets emitted from either the sprinkler system or the water mist system, and that will be of a beauty in the later stage. So as I said, it's used to track individual droplets or group of particle clusters. So we basically combine a lot of droplets into a group of the droplets. We see, okay, we assume they share the same property. You can just imagine it as a topic capsule, something like that. So the second phase of droplets does not necessarily share the same velocity, temperature, mass, whatever. So as I said, it's a secondary phase. So it's ideal. The beauty of it is ideal for capturing characteristics of the droplets and the sprays. So the trajectory, basically the movement of the history, and the temperature, the mass, the volume, the diameter, anything you can imagine of that droplet, we can track them throughout the whole life of the droplet as well. So there's a bit of a background knowledge, and we will utilize this methodology, this beauty, in the later on stage. So to give you an idea on how this water mist and sprinkler system perform when they try to suppress the same fire, that's what we do with fire dynamic simulator, FDS. Basically, you can see a fire starts. We put in, I believe this one is for sprinkler system. It basically suppresses the fire within 15 seconds. This is a very small design fire, and we basically activate the same, activate the fire suppression system at the same time, 10 seconds here as well, for both water mist system and the sprinkler system. So on the bottom hand, you can see on the left-hand side, this is the performance of water mist system. Right-hand side is performance of the sprinkler system. So what we did is we deliberately controlled the droplet size, varying from 100 micrometer to 200 micrometer to represent a bandwidth of the water mist system. And we find actually within the bandwidth of the water mist system, it actually performed pretty well, saying they have a rapid cooling, suppressing the fire within like 5 to 10 seconds very quickly, and it sustained the fire suppression. But for sprinkler system, we see that even we activate the system at the same time, 10 seconds, but actually it takes a bit longer compared to water mist system, although it's also good enough, but it just takes longer once we increase the droplet size. So basically this is from 1,000 micrometer to 2,000 micrometer. we can see once we increase the droplet size from 1,000 to 1,700 to 2,000, the time it takes to suppress the fire or to reduce the temperature down takes significantly longer. So that's why we believe that, okay, there must be like I said, a significant difference between the fire suppression mechanisms. So what we find is actually the main fire suppression mechanism for sprinkler system are the direct heat removal, but for water mist system is about the evaporation and volumetric displacement, as well as the latent heat removal during its evaporation. Like we said, the latent heat capacity of water is around 2,256 at 100 degrees C. But if you still remember, the CP of water is only around 4 kilojoule per kilogram. So that's a significant difference just by heat removal. But we have to know as well that the evaporation actually produces a large amount of water vapor. Actually, the volume difference between before it evaporates and after it's evaporating, it's huge actually as well. So it repels the fuel away from the flaming area. It repels the oxygen away from the flaming area as well. So we say that this is a different mechanism. This is why water mist system is better than sprinkler system in terms of their fire suppression. But what we find later on is what about the efficiency as well, or effectiveness of utilizing water? Because we know in some scenarios or in some setups, say like you're on a plane or you're on a ship, you don't really have access to tunnel, you don't really have access to infinite supply of water. So, okay, what do you do? Is there any way that we can quantify the efficiency and effectiveness of the water utilization? So that's the second work we worked on. Excuse me. We call novel stochastic approach of analysis on water mist and sprinkler system. So this is a experimental study that we referred to by some researcher back in China, Huazhong University of Technology. Pretty good. So basically, they have this small chamber. They lit up a pan of fire here. They have a water mist nozzle on top of it. So basically, we cross-validated our experimental setup, our simulation with the experimental setup provided by the Chinese researchers. So this becomes the interesting part where we're talking about every droplets being tracked, the mass, temperature, diameter, and the history of the droplets are available, basically tracked during the whole life cycle, at the instance of it burst to the instance of it basically hit on the wall or totally evaporating, basically tracking the whole life of the droplets. So another beauty of this computational fluid dynamics CFD is you see something you don't really see in experiments, basically on the microscopic side. So on experiments, what we can measure is basically the spray pattern, the temperature regions, temperature readings, velocity probably through PIV technologies, but you can't really see how many of the droplets or how much of the water has actually been evaporated, or has it actually been actively contributed to the fire suppression. So that's something you can see via the CFD approach. So that's what we say by macroscopic and macroscopic. I'll show you soon. So macroscopic, as we said, we can see the temperature, we can see the flame shape during its growth period, 2 seconds. It's basically fully developed, small fire as well. And the suppression as well, basically after 2 seconds, we activate the water mist system, and basically that suppress the fire. That's something we can see and we can validate against our observation in experiments as well. It's validating good. We see the fire being suppressed, the temperature being reduced, the plume being tilted away, something we can see. But this is something that we can't really see during experiments is, like we said, the efficiency or effectiveness of the water utilization. So this utilization rate concept, I basically kind of imagined it or invented it. So how I define this utilization rate is, like we said, we are tracking each and single one of the droplets. So if you can imagine one of the droplets, assuming at its burst or at its emission from the nozzle itself, let's say it have 10 grams of the initial mass, for example, or 1 gram, depending on how big the droplet is. And at the end of its life, either it's fully evaporated during the fire suppression, or it's basically hit on the wall, hit on the ground. So let's say at the end of the life, say it hit on the ground and we have 5 grams left. So we know basically the mass loss of the droplet is 5 grams. Initial mass of the droplet is 10 grams. So we have the utilization rate of the droplet because we know that the mass loss from this droplet must be from the evaporation. And that evaporation have to be basically contributing to the fire suppression, letting us to know basically that amount of water is basically evaporated, taking such amount of heat away from the fire. So that's the concept of the utilization rate. So with I1 equal to 1 to n, basically we take the sum of every droplet we track within the domain on top of the every droplets we inject into the domain. So the results are summarized in the table. We find that, okay, the water mist system and the sprinkler system, if we compare them and different conditions, the efficiency or the utilization rate of water mist system can be as high as 13%, but the utilization rate of sprinkler system can be as low as 0.19%. So basically what that means is that as high as 13% of the water you basically put into the fire suppression can be very effective. But for sprinkler system, it's probably only 0.19% of the water is actively used during the suppression, or actually contributed or evaporated during the suppression. So that's, again, validated our idea on the sprinkler system basically takes the heat away by CP, by heating up the water droplet, not evaporating. So that's the beauty of Eulerian-Lagrangian, and something you can see. So that's basically the end of the suppression part. I'm not quite sure if you have any questions to ask right now, or you want to leave all questions to the end, whichever way you like. I didn't hear anything yet, so I assume we can put everything to the very end QA. So coming into play, here are the 2 cases or 3 cases that we use apart from pure research, but something we can use in real engineering work. So radiation heat flux and all the smoke movement. This is a project we're currently doing in FRNSW, so in-house project, due to the kind of the NDA or the IP issue. I'm not going to tell you which building it is or where it locates, but this is a rather small model. So basically, we are only looking at 2 rooms of the whole building that we are basically capturing the issue of basically the area of interest we are looking into. So the problem here is that we have a non-compliance with the BCA. It's a spandrel. It's basically this fire probably can start from a lower level. And we have a opening on the wall here, and we have an opening on the upper level. And this spandrel is not high enough, or it's not, and this horizontal projection is not long enough to be BCA compliant. So there is a risk of fire being developed here, and the fire can penetrate, can extend out from this opening of the door here. And there is a potential of the fire re-entering on the 2nd level. Or if the fire doesn't really re-enter on the 2nd level, there is also possibility on the fire or the smoke heat here, emitting radiation to the 2nd level opening and basically causing a fire inside as well. So the client is asking, or they want to ascertain whether or not this current spandrel setup is good enough, or can we say it's DTS, or can we say it is a acceptable solution, that there won't be a too much of a fire, or there won't be too much of a heat radiation up basically above the level and basically coming into the second room. So we're saying only the area of interest is modeled, is simulated, and we have 3D smokes and temperature slices, variability slices to help us aid and basically ascertain the level of radiation or level of temperature, whether or not they are dangerous or not. Like we said, flash dynamic simulator, and we put a 2.5 megawatt medium gross T² fire, and we basically run the simulation for 10 minutes within this computational domain. So on the left-hand side is two animations. On the top, basically, you see the fire and the smoke. And on the bottom, you see the temperature. On the slice, basically, the slice on the doorway are basically on the opening as well. And on the right-hand side is basically the radiometer readings we basically put here. So you can see the conclusion first is within 10 minutes, the radiation didn't really reach to an acceptable level of reaching up to 13 kilowatt per meter squared or 25 kilowatt per meter squared. We only basically limiting it to around 1 to, even it's actually below 2 kilowatt per meter squared. So we think, okay, this is not so bad scenarios that we can say the building up level is safe. So you see actually the smoke basically occupied the whole ground level or level 1 within 5 minutes. And you see smoke basically coming out from the domain, sorry, not a domain, coming out from this window as well. And you see the temperature from the bottom as well. You see a hot plume coming at basically standing outside of the second level. But the temperature here is not as high because there's no direct flame coming up. It's just basically temperature from the suit itself and from the smoke itself as well. So the radiation from that smoke is not that bad. So that's one practical application that we can utilize the computational fluid dynamics approach to see whether or not it is good enough. And this is actually giving us pretty good confidence that, okay, given this scenario, we can say this is DTS or this is good to go. We don't really have to worry about this schedule here, although it's not compliant. That's basically after 10 minutes. That's a small case. The next case I'm going to share with you is a bit of a larger one, smoke movement. Same thing, it is still a Fahrenheit Global in-house project. Not going to tell you which one it is and where does it locates, but compared to the previous one, this one is a pretty large domain, pretty large scenario. We have a 10 actually levels of a hotel, and the building is still under construction. So we don't have this building ready yet, so we can't really do any testings on site. We have to do this simulations. So the problem here is that we have two lift shafts here, 1, 2, serving lift 1, 2, and serving lift 3 and 4. And the client is basically wondering whether or not the fire starting in ground level will leak through, or the smoke will leak through the lift shaft, and whether or not they penetrate or affect the upper levels. And the problem here we find later on is that on level 4, these two lift shafts have a common opening on level 4. So basically lift 1 and 2 have an opening on level 4, 3 and 4 have an opening on level 4. This is the only level that these two lift shafts can talk with each other. So we find actually there could be possibly a problem there. I'll show you that later on soon. And the complexity comes as well is that whether or not, because this building actually is subject to wind, there is basically a strong wind blowing constantly against the building, against the opening and the doors. So the clients want us to ascertain basically whether or not the wind will affect on the smoke movement as well. So this is also another good example on CFD as a good tool to assess the effect because we don't really have the building yet. So the model looks a bit more complex here, but we still simplified a bit of the model. We're only modeling the area of interest. So ground level and three levels up, and the shaft as well. So the lift shaft with the leakage modeled. So this leakage actually is the lift shaft leak. Per requirement of any lift shaft, you should have a leak on top of the lift shaft. And similar leaks are also available on the floors where they open to. So you probably don't really see it here, but the idea is that they still have such a leak, the leak. They are ground level, level 4, level 5 and 6 probably as well. So like we said, we have wind blowing towards the building here, and you see a door opening here. So we have two scenarios modeled. One is the door is closed. We don't really have the door open at any time. And another one is basically the wind is blowing and the door is triggered open by the smoke detector above the fire. So the concept here is once the smoke detector receives a signal that the smoke is above 7%, you will trigger the door to let the door open. And here comes the question whether or not the wind will actually blow in through the door and prevent the smoke to escape from the door itself. So similarly, let's have a look at the results. So I'm showing you visibility, smoke, and smoke as well. So visibility is something we can see through CFD as well, so we can know, okay, how badly is these levels affected by the smoke. So basically the darker color towards red basically means you can't really see anything. That's 0 meter visibility. Towards the bluish level basically means you have a clear view. So you see on the lift shaft, I have a slice there, basically here. So the slice is on here. So you see whether or not the smoke has been penetrated through the lift shaft, whether or not they are affecting the lift shaft or upper levels. Probably you should be paying a bit more attention on level 4, this level, on the visibility and the smoke later on as well. So this is the case that we have the door closed. So if the door is closed, you will see actually this is a really bad design, because you see already the smoke penetrating through leaking through the leads of the lift into the lift shaft. And here visibility you can see as well. And on level 4, it actually leaked to the level 4 doorway as well. You see as well most of the smoke leaked out from the lift shaft leak, like we said before, per requirement. So basically it went out as well. So you see on this time around 450 seconds, the smoke actually penetrates to another lift shaft. That's because basically the two lift shafts are connected to the ambient. So they basically have a pressure difference. They have a lower pressure inside the lift shaft, higher pressure in the fire cabinet. So allowing basically the smoke to penetrate through. So you see the smoke here as well, and you see the smoke basically coming out or leaking out from the top of the lift shaft. So that's really a bad scenario. The worst case scenario is that if we don't really open the door, the upper levels will be affected definitely. So we're saying, okay, let's open the door. Let's say trigger the door open after the 7% threshold is being triggered by the smoke detector. So similar setup, but this time we have a small door here. As we said, it will be triggered by the smoke alarm or smoke detector above the fire on 7%. So at this point, you may or may not notice around 60 seconds, the door is being opened. And you see actually the wind blowing inside as well later on. Same thing, visibility, smoke and visibility. I put the visibility here to basically show you that the smoke is being pushed in, but they cannot really push every smoke inside, because basically you see the smoke coming out from here being blown away by the wind as well. Under this scenario, we basically see, since we have the door open here, it's actually being connected to the ambient, to the environment. So there should be no pressure difference between the no such big pressure difference between the fire compartment, which is ground level, and the lift shaft, so we don't really see smoke penetrating or leaking through the lift shaft. So this way, we basically ensure the upper levels are not really affected by the leakage on the lifts. So basically, on the right-hand side, on the bottom, you see already smoke coming out from here. You see smoke coming out from here as well, and you see the wind trying to blow out the smoke inside. Basically, you see some smoke coming from this way, but it cannot really prevent the smoke escaping from the doorway. Most of the smoke still escaped from the doorway itself, so it doesn't really enter the lift shafts themselves. So that's why we say, okay, we recommend our clients to definitely have some openings on the floors. We definitely have some interlink on the smoke detector and the door opening. So definitely not close the door itself. So we keep the upper level safe.
Sorry to interrupt. Just at this moment, would you be able to just describe once again
Yes.
the difference between visibility and smoke?
Okay, so visibility is something we can, which is a very good question. Smoke is something, it's soot density, so we can visualize how badly is the area basically being occupied by smoke. It's more intuitive, but visibility is something we can quantitatively use, and in basically our fire engineering report, say this level of visibility is already deduced down to 10 meter, 20 meter, or 5 meter. So we can quantitatively know and quantitatively a certain level from any location, but smoke is basically a visual aid, more of a visual aid. So we
okay, thank you for that. Yeah,
not a problem. Thanks so much for asking that. That's a good question. So that's the second case that I want to share with you within Fahrenheit. So the last and foremost one is the application of CFD, how we use that in an arson fire scene investigation. So a bit of a background here is that there was this tragedy in 2011. There is an arson fire in Quakers Hill. I believe everyone here probably knows the tragedy here. So we've, at that time, been asked or being approached by FRNSW and New South Wales to conduct a collaboration on the investigation of the fire scene. Say basically how does it happen and why basically this fire started and propagated through the whole building or the whole room in very short time. So my supervisor there at the time, Dr. Anthony, was assigned this task, and basically we went into the experiment with FRNSW New South Wales, and we developed our model itself to basically try to see what's really happening after the scene. So we have included the combustibility of the lightweight polymers as building materials, basically the mattresses, the sofa, the wardrobes available in that room itself. But this basically leaves us with these challenges on how to accurately characterize the actual pyrolysis of these materials, but that's something on research, but I won't talk too much about that. So the ultimate question posed to us back in that time is what caused such a disaster within such a short time? So as we said, we've done a collaborating experimental study with FRNSW New South Wales. This is the experimental study we have. We installed thermocouples around the whole building, around basically the room itself. This is the experimental data we obtained at the time. And we used this experimental data again to validate our simulation model. So we want to make sure that our simulation, our model is doing the right thing, is reflecting the right physics. So basically this is our model. And we have, like we said, thermocouples everywhere. And at that time, we have fire damage insulators, FDS version 5. Right now, we have version 6, a bit more advanced, but same concept, similar ideas. So we have these beds, we have the chairs, the drawers, thermocouples, and we replicate in the same room in the simulation world or in the models. That's our basically mesh setup. We have a window here, which will play an important role later on. We have our thermocouple trees. We have, it's not, okay, sorry. The window, basically we find the window breaking in accordance to the time measured in the experiment. And this one actually is the critical rule or the critical factor that caused this fire breakover. We have two T-squared ignition sources set up on two beds. That conclusion or that recommendation is given to us by FRNSW. After basically the fire scene investigation, they identified this arson fire. They the criminals there lit up two fires at these two locations. So we basically replicate the same thing in our simulations. And here is basically how we incorporate all these material properties into our model. Probably too complex, probably too much information. I don't want to really dive into too much about here. So to go to the results or to the visualization itself. So this is a pre-flashover. We see actually it sustained for around 10 minutes after the fire started. But the problem here, or the thing we see here, is that within this 10 minutes, these two fires are sort of confined or sort of not developing to the other areas or not propagating to the other drawers or beds or whatever. But things happen here is that after 10 minutes, after 560 seconds, these windows broke because it's basically glass and it just broke. And that allowed for fresh air to come in, which caused the flashover, which you can see from here. Within 150 seconds, basically the fire or the flame flashed over and propagated to the whole room. So that's the reason, or that's the phenomenon we want to see. And at the time, we don't really know what's happening, but this is basically what our model tells us is once the once the window breaks, the fire actually propagates to the whole room. And after it propagates to the whole room, it basically burns away everything we see in this room. As anything that it can burn, it burned. So you see the beds burned away, the wardrobes burned away, the drawers burned away, everything. So that's between 10 seconds to 10 minutes to 20 minutes. This answered our question, what really happened or what is really causing the fire to propagate in this room in basically such a short time, within 20 minutes, everything's gone. And by observing the heat release rate, or basically the energy amount released here, we answered the same question. Pre-flashover, it's basically sustained below 2000 kilowatt to megawatts. That's pre-flashover before the window break. But once we see the window break, basically the fresh air coming in through the flashover period, it caused a significant growth in the heat release rate to around basically 12 megawatts. And it's sustained until it burns everything away, a slow decay. That's a post-flashover stage. So my supervisors actually, in collaboration with FRNSW, will successfully use this simulation and used what we find during the simulation as an evidence to the court to actually accuse the criminal to put him actually into jail. That's according to my supervisors, for the first time, this is a practice in Australia. So after that, we went towards a sort of a better world. Also, it's a lesson to learn from a tragedy. After that Quakers Hill's tragedy, FRNSW and the government actually made a requirement of automatic fire sprinkler system, which comes back to where I started my PhD, right? So for them to be mandatory in our residential aged care facilities after this tragic fire. So we did contribute a little bit towards a better world as an engineer and as a researcher. So that's basically the end of my major presentation today. Thank you so much for your time and your interest. And a bit of an advertisement for myself as well. If you want to know a little bit more about CFD, but not necessarily in fire engineering, but in some other research areas, I have a guest lecture next week, just next Thursday as well, at UNSW, 9 a.m. And if you are interested, feel free to drop me an email on either of these email addresses. Should be fine now. Thank you so much again, and I'm welcome or open to any questions.
Excellent. Thanks, Henry. Thanks for presenting that to us this evening. If there's any questions, feel free to unmute yourself and ask in an orderly fashion. I guess there's no questions there for you, Henry. Oh,
Not yet.
Mark.
Paul said, yep.
Yes.
Mark. Oh, yep, Mark. I've got a question for Henry. Henry, what's the strangest material or most or most out of place material, I think, that you've ever had to model in one of these sorts of things?
In the actually very good question. In the modeling world, is basically what we tell the model to do whatever we tell them to do. So in your question, reflecting back the sort of the material properties are the things here. The challenge here is we have to know basically how the material burns and what's the burning behavior. So basically, what's the heat release of the material and what's the combustion byproduct, and basically how long does it burn, and how fast is the chemical reaction taking into place. So that's why we have this complex equations here to basically incorporate this behavior of the material to coming in. So we have to ascertain the material behavior to be able to input them into the model itself. So the challenge here is really not too much about how to model it, but on the other hand side is how do we know how does the material burn? So basically we have to get the material property of the burning behavior of the material through experiments, which we do have access back in UNSW and back in other places as well. So we can burn the material, know their property, know their burning behavior, and then we can take that information, put that in our model so that the model is doing whatever we want them to do accurately. So to say what's the most complex material, the challenge right now probably is about battery. We don't really know how to model a battery fire very accurately because the end product or the combustion product mostly are in gas phases, but we don't really know that the gas combustion byproduct are from the very first instance, or it's actually a byproduct or the product of a series of chain reaction. So we don't really know at the very beginning of the pyrolysis or very beginning of the battery fire what's actually being produced. We only know at the very end what's being produced. So there is a gap in between. So that's probably the most complex or the most difficult material we are facing at the moment. Because for the others, basically we know it's a pure material, say polyurethane, polyethylene, or any other, say like organic materials. We know it's a pure material, but for batteries, it's too complex.
And that's lithium batteries you're obviously talking about there.
Thank you.
Yeah.
The other problem with lithium batteries is it can cause multiple fires at the same time. So
Possible,
it
yes.
ejects gases and it ejects
Exactly.
projectiles. So it'd be very difficult to model a fire if there's 3 fires occurring at the same time in different areas of the room.
You have to know where does the challenge here is that you have to know where does it project the fire to, where basically it throws the fireball to, and whether or not it lands on something combustible or not. And as well, battery fires are behaving too much differently compared to a normal fire. Here is that the battery fires are often jet fires because basically the gas is only leak from a small crack or a long, say, crack from the edge of the battery. and it will actually lead to a fire plume or a fire jet, and we don't really know where does the fire jet starts as well, because we don't really know where does it crack. So that's somewhat of the challenges that we face for battery fire as well.
Yeah.
Exactly.
Are there any other questions? I think someone's got their hand up, but I don't know.
Luke, do you want to answer your question?
Yeah, that's me. Can you guys hear me okay?
Yeah, I'll do it.
Yeah, great. Hey, thank you for the presentation. Very, very interesting. I just had one question about your forensic modeling of the Quaker Hills building. So, and apologies if I've missed it, but so it appears you did some experimental burn and then also some FDS modeling with,
Yes.
looks like some pyrolysis modeling in there, which is very nice to see. With the window breakage was obviously a significant event in your
Yes,
FDS model. Did the experimental burn, did that have a window in it as well?
Yeah, exactly.
And did that pop out at the same time? I mean, did you adjust your window breakage in the FDS to be the same time as the experimental window breakage?
Exactly. So that's basically the sort of the limitation at that time, basically 10 years ago, is that we have to ask the window to break at the same time as we observed during the experiments. So the answer is yes, we do have a window installed during the experiment as well. Basically, FRNSW did a very good job on replicating the same room. Basically, we have the same dimension, we have the same setup, the doors, windows, the layout of the room itself, everything is one-on-one. So we deliberately burned the same, sort of the same room. So we observed the window breakage at the time of 560 seconds. So at that time, 10 years ago, we had to tell the model, okay, the window breaks at 560 seconds. But right now, probably, I'm not quite sure yet, we should be able to actually, like I demonstrated a little bit earlier, trigger the opening of the window actually based on any parameter we observe within this model itself. Say, for example, if we know that the window will break at certain temperature, we can allow that to happen in our current model as well. So if we know it's going to be break at 300, 400 degrees C, measured at the window, we let the window break at 300, 400 degrees C. But since this is a more, not purely research, but it's more on a real life scenario, we want to use this as evidence. So we want to make it more accurate. So that's why we have the window break, or the window basically open at the same time as we observe in the experiment.
All right, thank you very much. It's again, a great presentation. Thank you.
Thank you.
Yeah, it's a fascinating presentation. Yeah, just to add on to that, it's very, very interesting. I think we could provide some challenges to you to take a look at for us as well sometimes.
Yeah. I'm
sure they're all a challenge, right?
There are so many challenges in both research and real life. Anyways, it's good to be an engineer to solve challenges.
Yeah, and how difficult is it to match up the theoretical world and the real world on some of these instances?
In terms of the modeling, let's say it depends on the complexity of the scenario. Like we said, if we know what's happening, it's not so hard to actually align the simulation world and the real world. What I mean by we know what's happening is you know what you're burning. Reflecting back to the battery case is, if you don't really know what you're burning, you can't really tell the model to basically to burn what you're burning. So that basically is a gap. It can cause you the misalignment between the simulation and the real world. But if you basically set up the boundary condition correct, like I said, if you know there is a wind blowing, but if you're not modeling the wind in your model, if you're not telling your model you have a wind, of course that there will be some error, or there will be a misalignment, as well as how careful you construct your model. As we said, computational fluid dynamics, you have to know your model. And the more important or more practical one is you have to know what the mesh density or the mesh size you want to put into your model to a certain level of accuracy. If you basically set up your model very poorly, it's not the correct fire, it's not dense enough, or basically fine enough to mesh, you cannot really capture the fire behavior. There is a risk and there is a possibility of your model basically giving you a very garbage result. Basically, a golden word in our simulation guides is garbage in, garbage out. So if your model is not correct, you shouldn't be really expecting your results to be correct. So before using the model, we have to be a bit careful on a certain basically knowing what we are doing. So we know what we are doing should be right, and we should be expecting our model, our simulation to be right. If there's any misalignments, that's very often we see between our model and the real world, we have to go back to our model to see, is there anything that I missed? Is there anything that I set up differently compared to the real life scenario? There must be something either we set up wrong or there's something we missed. So there is a risk of that. So you shouldn't be taking it for granted, say, okay, I'm just putting in whatever I think I'm putting in and the results should be reliable. That's not necessarily the case.
Okay, yeah, no, that makes sense, of course, yes.
Any other questions? All right. Thanks, Henry. Thanks for presenting for us tonight.
Thanks
and
so much.
Just want to remind everyone, yep, there's the call for abstracts for the conference in October. So if you have a presentation you would like to present at the conference, please submit an abstract, and don't forget that the conference is on in October this year. If that's it, I'll let everyone go and we'll stop recording, and thank you everyone
quick
for
question
attending.
here, sorry to interrupt. Where does the conference hold? Is it in Sydney, online?
It is, sorry, it is in Sydney. It's in Penrith, to reduce the cost, because if it's in the middle of the city, it's going to cost a lot more. So yeah, it's in Penrith this year. 21st, I think, of October it starts. It's a Monday through to Wednesday, but you can find all the information on the AFI website. All right, appreciate it, guys. Thank you very much.
Thanks, everyone.
Thank you, Mark.
And I
Henry.
hope I've answered all the questions. If there's any unanswered questions, please feel free to drop me an email. Very happy to discuss on that.
Yep, will do. Thank you very much once again.
Thank you so much. See you guys. Have a good night.
Thank you very much.